Welcome to another session on analytics with Excel. In these sessions, what we are doing is considering statistical methods, statistical techniques that are used to analyze, summarize, and predict using data. And the specific tool that we will be using is Excel to demonstrate these techniques. The techniques that we have covered or have started to cover so far involve descriptive statistics, where we speak of measures or calculations from data that describe central tendency or location, or variation in the data, or various aspects of shape and descriptions of data that help us understand what the data looks like or can be summarized as. This is usually done by analytics or analysts in the context of what is called descriptive analytics, which is a slight generalization of the idea of descriptive statistics. And you will see more of descriptive analytics in visualization sessions in the future. For our purposes, we shall be looking at statistical measures that speak to various summary statistics of the data. We have already referred to measures of central tendency, such as the mean, which is the average of the data. The average here referring to the simple addition and then division by the number of observations. For example, the average or per capita income. We have referred to the median, which is the income of the average person, so to speak. Sort, arrange, pick off the middle, with the slight caveat of a little calculation being done if the middle is even. One also refers to the mode, which is a most frequent value if such a value exists in the data. Moving on, we now talk about dispersion. Dispersion refers to the idea that the data is not localized at a single value. The mean and the median refer to single point summaries of the data that say, if you give me a number, what is a representative number? If I want to understand how well off Indians are, a per capita income or a median income gives me a single point description of the income of Indians or those in any particular region of the world. However, that is not all the information that is there. Not every citizen of a country has the same income. Therefore, we speak of dispersion or variation. And the simplest way to speak of dispersion or variation is to talk of the lowest and the highest. In other words, to speak of the range. As we have noted, x1 is the smallest number and xn with the parenthesis is the largest number, and the range is simply the difference between the two. If there is no dispersion in the data, then the range is 0. If the range is 0, the only thing that can be true about the data is that all the observations are the same, which means x sub n minus x sub 1 is equal to 0 because x sub n is equal to x sub 1. Therefore, every observation is equal to the mean, which is equal to the median, and therefore there is no distribution at all. So the smallest value of the range is 0. A large value of range indicates that there is a big difference between the largest and the smallest. For example, the largest and the smallest income. So, if we go back to a data set that we have been considering, Recall the data set that we had looked at, which was a data set of stores. And we had considered variables such as area, items available, and customer count and store sales. We had computed descriptive statistics of customer count or store sales. And those descriptive statistics are reported here. Just to remind you of where those descriptive statistics came from, let me delete these sheets. And ask for data analysis again. Remember, the tab data analysis should be there in your Excel. If it isn't there, you will need to add it. Let me ask for daily customer counts. And request it in a new worksheet together with summary statistics. The range is 1460. Where does this come from? The minimum is 10 and the maximum is 1470. If you see the sorted column, the sorted customer count, the smallest is 10 and the largest is 1470. This is reported out in the descriptive statistics as well. The range, therefore, is 1460, which is the difference in customer count between, shall we say, the most popular store and the least popular store. This gives an immediate perception as to how variable the stores are around, for example, the typical store, which has 775 customers. So this is our basic measure of dispersion or variation in data. As you might guess, there are certain challenges with this. For example, if there is a particular store which sees many more customer counts, let's say 2,000, then the range will increase, even if it is only one store. So the range suffers from a problem that we spoke about for the mean as well, that it is extremely susceptible to the tail of the distribution. It is driven not by the entire data, but by the minimum and the maximum only. And therefore, it has no reference to shape whatsoever. This causes certain analytical and interpretation difficulties with the range. So therefore, statisticians have alternative ways of speaking about variability. One of the commonest measures of variability or variation or dispersion is the notion of a variance. The notion of a variance requires a little bit of thought. However, the idea behind it is not very complicated. Recall what X bar was. X bar, if we go back on our slide deck, is the mean of the data. Take all the observations and divide by the number of observations. This is the average. Variation or dispersion, in its commonest sense, asks the question, how far apart is an observation, let's say the first observation or the ith observation in general, from the average? How far away is a random observation, if you want to think of it, or any observation from the average? That is measured by xi minus x bar. Xi minus x bar. However, when we talk about variation, we tend to think symmetrically or equivalently about being above the mean or below the mean. Variation can be because a number is high or because a number is low. Therefore, simply looking at xi minus x bar tells you the difference between xi and x bar. However, it also indicates whether xi is more than x bar or xi is less than x bar for all the observations. And this is a distinction that I do not, or we do not want to make when it comes to thinking about variation. So we remove this distinction by taking squares. Remember what the square of a number is? The square of, for example, 2 is 2. But the square of minus 2 is also 2. So if xi is 2 units away from the average, that contributes to, I should actually say, 2 into 2, which is 4. And this also is minus 2 into minus 2, which is 4. So if it is 2 units away, then it will contribute 4 in this summation. And if it is 2 units away on the other side, which is on the minus side, it will contribute 4 as well. I've ignored the idea that certain observations are above and below and simply said certain observations are far away from the mean. Now I divide to take an average over all my observations, and I divide by n minus 1, which is a slight peculiarity in the sense that there are n observations and I'm dividing by n minus 1. This is done for a variety of technical reasons. One easy way to remember is that if there's one observation involved, there can be no variance because there is no possible variation that I can measure from one observation, which is the average. So the average, so to speak, accounts for one observation. And in the sense of degrees of freedom, as statisticians say, I'm left with n minus 1 observations around it. Hence the n minus 1 division and the average squared variability around the average itself. Because of the squaring, the variance is in units of currencies or squared currencies. So for example, the variance of income is measured in squared rupees or dollars or pounds or euros, whichever currency you wish to look at. But it is not in the units of the currencies itself. The variance of height is in squared inches or squared centimeters. So variance as a measurement is motivated by the idea of average dispersion, but it is on the wrong scale. To convert variance to the right scale, we take a standard deviation version of the variance, which is exactly the same as the variance with the square root on it. So what is the standard deviation? The standard deviation is the square root of the variance. So the standard deviation of income is now measured in the currency itself. So if the income is in rupees, then the standard deviation is in rupees, much as the mean is in rupees and the median is in rupees, or dollars or cents. So therefore, the standard deviation is a measure of variability on the same scale as the mean and as the observations themselves. The calculation of the variance and the standard deviation can be done from first principles if one so chooses. For example, we have mean customer count that we had computed, actually in two ways, as the sum divided by the number of observations and as the number of observations itself. And then what we can compute from the customer count data, let us say, is the deviation. So for the deviation, what should we do? Take the observation here minus, let's say, the mean, which is here. Minus 271.1, which is the difference between 530 and 801. It is a negative number because 530 is less than 801. In order to carry this formula through the cells, I will need to fix the cell for the mean and pull down the formula. Which gives me the deviations. Some of these deviations are positive, some of these deviations are negative. In fact, as you might guess, the total deviation is 0. And you may check that if you wish. The squared deviation is simply the square of the corresponding number from where we can calculate our variance, which, if you recall, is in the first order of business the sum of the squared deviations divided by the number of observations minus 1 the standard deviation is equal to the square root of the variance. $292, the variance is 85,741 odd. If I go back to my summary statistics, the sample variance and the standard deviation are available to me in the descriptive statistics summary. So the calculation that I just showed you illustrates the computation, but is unnecessary given the availability of the data analysis toolbox in Excel. So therefore, the standard deviation of 292, which is An average deviation, shall we say, from the average, which is 801, is computed directly from the descriptive statistic summary. There is a challenge in what the standard deviation actually refers to. And before we get to explaining what the standard deviation refers to in terms of an interpretation, we need to talk a little bit about certain other measures of dispersion, shape, and structure that will give us boundaries within which to talk more about data.